Hi, my name is Harley Phillips. I'm the Asphalt HMA Technical Director. I've been with NDOT approximately 29 years. When I started my career, I was a laboratory technician, which I really enjoyed, and I still try to get in the lab as much as possible. Today, I'm going to talk about calibration and verification of our testing equipment in general. Starting off, we deal with balances, which are a 12-month frequency. As you can see, most of these items here are on 12-month frequencies. We typically like to have our technicians do this stuff in the winter months when things are slower. A little bit of terminology. Accuracy is the degree of conformity of a measurement with the true value of the quantity measured. We also have off-center errors, the differences in indicated weight when a sample weight is shifted to various positions on the weighing area. To perform this, you will need a balance, naturally, and you'll need a set of certified weights. These weights are to be NIST traceable. The weights shall be a minimum of Class 3 for use on G2 and G5 balances. G20 balances require Class F weights. These weights are required to be checked every 12 months. Here we are with the balance. It's kind of hard to see, but if you could zoom in on our balance, it's a Mettler PC16, which represents approximately 16,000 grams. To start off, you want to clean the balance and standard weights with a lint-free dry cloth. A lot of times we'll use gloves because the oils from your skin can get on these weights and affect the weight itself. You'll want to have a thermometer and let it get to ambient working temperature. Typically, we'll place the thermometer near the balance, leave it there for half hour to an hour possibly. When we start this off, as I said earlier, this is a PC16, which represents 16,000 grams. Okay, as you can notice on the balance, it's at 1,500 grams. So we don't have a perfect world, but it's pretty close. So we start off in 10% increments of the capacity. So for this, 1,500 grams, in a great world, it would be 1,600 grams. We're going to take it. All right, as you go through, you're going to increase this by 10%. So you see the top right, we got 3,000 grams. Bottom left, 4,500. Bottom right, 6,000, and so forth. Here's the form we like to use. If you can notice on the left where we've increased by 10% and we took this up to 15,000 grams. There's also an off-center error where we like to check different areas of the balance. To do this, you're going to use approximately half the capacity of the balance, which as you can see is 8,000 grams in the middle. And then we will place it on each corner. So at the top left, it's 8,000 grams, beautiful. On the right back, it was 99.3. Front left, and then the front right. This balance is well within, as you can see on the paperwork. There is tolerances for this. The accuracy of 10% interval shall be equal to 2/10 gram or 1% of the test load, whichever is greater. On your off-center error, the maximum shall be equal to or less than 0.2 grams or 1/10 of the test load, whichever is greater. For G5 balances, any 10% interval shall be equal to 2 grams or 1/10 of the test load. And for your off-center, maximum shall be equal to or less than 2 grams or 1/10% of the test load. Here we have G20 balances equal to 5 grams or 1/10% of the test load. For your off-center error, it's less than 5 grams or 1/10% of the test load once again. All right, we will now move into calipers, which is covered by ITM 916. To perform the caliper check, we use the 1, 2, 3 blocks that are in the plastic bags and then our calipers. Here's a certificate of NIST traceability for the 1, 2, 3 blocks. And here's the form used for verifying the calipers. We would check the 1-inch outside dimensions. So this is right on the money. We check 3-inch outside dimension, and we check 6 inches. We will come back and do 1-inch inside dimensions, 3-inch, and 6-inch inside dimensions. Here's our verification form, which is found in the back of ITM 916. Pretty straightforward stuff we do here today. All right, we will check our sieves. Very important to have your sieves checked. This is covered by ITM 902. We're going to verify the physical condition of testing sieves. As you can see, we have black lines on there. It helps us identify the area we are going to check. They intercept each other. For this, we will use them calipers that we've just verified. We need to identify the sieve, and this is for the number 4 and coarser sieves that we do the check with calipers. This is a 3/4 inch sieve, approximately 19 millimeters, USA standard testing sieve. All right, for the coarse sieves, we're going to check to see that the frame is not cracked, welds are not broken, the wires are tight, and no irregular openings. So once again, there's our sieve on the left. There is a device called the go, no-go gauge that is approximately used for a quick check. Here we have a diagram of 5 X components intersected by 5 Y components. We will check side to side and top to bottom and write down the readings. On our form here, you can see we have 10 X components and 10 Y components, which we will average. This is permissible openings for the number 4 and higher sieves and a maximum individual opening. For the sieves finer than the 4, it's pretty much a visual. We like to hold the sieve against a uniform illuminated background. You want to check for cracks in the frame, broken solder joints, weaving defects, creases, wrinkles, wire tightness, and irregular openings. A lot of times the solder joints can be broke. Years ago working in the lab, we were wondering why are we getting so much material passing the 200? Well, as the shaker goes, that lip had broke on the solder joint and the material was sliding out at the side. So you gently want to place your finger around this just to check to see if it has been broken. You want to look for too much material staying in the sieve. If it's a dirty sieve, you want to replace it. If you see any kind of weaving or bowness, you definitely want to replace that 200 sieve. All right, now that we've verified our sieves, we're going to check our shakers, which are covered by ITM 906. For this, you're going to need a stack of sieves and a timer. On the left, we have our timer, and then we got our stack of sieves. All right, you'll need a balance, and you'll need a pan and a lid for your shaking. Initially, we will check our timers. As you can see here on the left, the timer was used. It stopped at 5 minutes, 0.78 seconds. And on our shaker, it actually stopped at 5 minutes. So this is very good. We're going to repeat that for 10 and 15-minute intervals. Here's on our paperwork. We've made the documentation for the times. Timer shall be within 5 seconds, plus or minus 5 seconds at 5 minutes, plus or minus 10 at 10 minutes, and plus or minus 15 for 15 minutes of shaking. All right. So we typically, in the asphalt world, we use 12-inch sieves, but 8s can be used. You just don't have as much area. So you want to determine a weight and record it. We're going to put in 1.5 inches to number 8 for the coarse aggregates, and we'll use the number 4 through the 200 for our fines. Shake blended ags for 10 minutes, and the sands will be for 15 minutes. Typically on the 5-minute shake, it's for coarse aggregates only. All right, you want to take the first sieve that retained material, put a sieve in there, cover the lid in the pan, and you're going to shake for 1 minute by holding in a slightly inclined position. Strike the sieve sharply with the heel of a hand at 150 times per minute. You're going to rotate the sieve about 1/6 of a revolution at intervals of 25 strokes. Weigh the material that passed the sieve and retained in the pan. Then you will weigh the material retained on the sieve. You're going to add the weight retained on the sieve and the weight passing the sieve to verify that the sieve was not overloaded. If the sieve was overloaded, the verification is void and you'll need to get a new sample and start this over, which most people do not like to do. Here you can see the sufficiency of the sieves. No more than 0.5% by weight of the total sample shall pass any sieve after 1 minute of hand sieving. You're going to repeat the procedure for the remaining sieve. If a sieve does not meet the tolerance, the shaking time shall be increased to determine an adequate time. As you can see on the timer and the shaker, this had to be shook 11 minutes instead of 10 to get that adequate shaking. We will now talk about thermometers a little bit, covered by ITM 909. On the left, we have a certified thermometer. We have an oil bath or a water bath. We like to verify the thermometer scale accuracy for our liquid in glass total immersion, liquid in glass partial immersion, dial type, and handheld digital thermometers. You want to record the manufacturer, serial number, any pertinent information on there, the date of the calibration for the certified thermometer. Liquid in glass total and partial immersion thermometers. You'll record the manufacturer, type, model number, graduation of the thermometer that's being verified. Visually inspect the shaft of the thermometer for air bubbles, separation of the liquid, foreign matter, glass faults, or any other apparent defects. You will immerse the thermometer being verified into a water or oil bath. Partial immersion thermometers to the immersion line. Total immersion thermometers would be to the point being verified. We will use a water bath for less than 200 degrees Fahrenheit. Oil baths are used for temperatures above 200. Immerse the certified thermometer into the water or oil bath. Allow the readings on both thermometers to stabilize and then record the temperature of each thermometer. Where there is a scale error in the back on table 1 of ITM 909, the thermometer may still be used if the difference is visibly noted and the offset is being applied during use. Here we have a dial type thermometer, which are put in the mix a lot of times. Record the pertinent information for that thermometer. A lot of times these do not have numbers on them, so we will label it with a permanent black marker of thermometer 1, 2, 3, etc. You will immerse the thermometer and the certified thermometer into a container of boiling water to approximately 1/2 depth of the container. Allow the readings on both thermometers to stabilize and record the temperature of each thermometer. For this particular type of thermometer, it shall be within plus or minus 5 degrees Fahrenheit. If it's within the 5, the thermometer may be used if the difference is visibly noted and the offset is being applied during use. Here we have a handheld digital thermometer, very handy. Once again, we'll record the pertinent information of this thermometer. We will also immerse it the same as before, but immerse the thermocouple assembly and certified thermometer into the water that it will be boiling at approximately half the depth of the container. Allow the readings to both stabilize and record the temperature on each thermometer. For this particular type of thermometer, there is a plus or minus 2 degree Fahrenheit difference. If it's within that range, you need to note it so everyone knows what the temperature reading is actual. Here we have a liquid calibration bath that we have at NDOT. All right, so now that we have a certified thermometer, we'll check our ovens, which is covered by ITM 903. We're going to verify the temperature settings. In this particular case, this oven is set at 110°C. To perform this verification, you will need an aluminum or a brass well and a verified thermometer. Here's the verification form we will use for this. As you can see, the oven has got its, we have commission numbers at NDOT, and that's been labeled at the top. Our manufacturer, the type of oven, and the thermometer that we are using. You'll place the thermometer inside the brass well and position in the center of the oven, top to bottom and side to side. Set your oven temperature. In this case, we want 110C, which is 230F. After the drying temperature for this is 110 plus or minus 5C. So when we put it in there for 1 hour, I recommend putting a note on the outside of your oven. If you share an oven with another technician, it's very possible you could start this process. Your lab partner could come in and open your door, which just sets you back, and you're going to have to start over. So it's a good idea to let somebody know you're doing this verification. Please do not open this door. All right, so after 1 hour, we had a reading of 102 degrees Celsius. Our range is 110 plus or minus 5, so we are not within the allowable range. We cranked up the oven a little bit to 120 Celsius. We checked it an hour and a half, actually a half hour after that, we were getting a reading of 112C. Another half hour later, we had a 110 plus or minus C. 110C, and then after the 2.5 hour range, another 110C. So we had 3 consecutive readings within the 110 plus or minus 5. This oven is good and has been verified. You need to put a note on your door that lets people know, your lab partner or anyone else that will come into your lab, this oven is set at 120C to achieve 110C. All right, we will now discuss vacuum systems, ITM 905. Here's a couple of setups. On the left was when I first started with NDOT. This was the way it was with the manometer. You can see the dry right in the flask in the back and our pump. On the right is more of an updated system. In the back is an auto rice, which controls the vacuum for you and will drain it off. If you notice in the middle, we have our pump and a pump saver, which it keeps water from getting into the pump. All right, here's a digital gauge and a mercury manometer. In the olden days, we had to read the mercury manometers, top and the bottom, and then we would add them together to get our actual vacuum. Now we have the digitals, which will have to be checked. Here we have the auto rice, which is a very handy tool. You can set it for the 15-minute vacuum pulling. It tells you where the vacuum is. You can pretty much walk away and do other things in the lab while this is going on. Maximum of plus or minus 2 millimeters of mercury offset for the digital vacuum gauge may be applied and is required to be clearly indicated on the gauge. We verify our core lock with the Torr gauge, which needs to be done every 3 months. There's a picture of a Torr gauge, and you can see that it's pulling down to about 4. The reading of the vacuum gauge used for AASHTO T331 shall be 10 millimeters of mercury or 10 Torr or less. Reading for the vacuum gauge used for 572 ITM, which is our drying, shall be 6 millimeters mercury or 6 Torr or less. Thank you so much for listening to my presentation.